In section 2.4, we're going to kind of build off of some of the important ideas that we actually talked about back in the very first chapter, as well as back in section 2.2. So back in the first chapter, we talked about the idea that vectors were an extremely important way to understand how to navigate throughout 3-space. And there are actually 3 very important sorts of vectors that we're interested in talking about as they relate to vector functions. So back in 2.2, we talked about the idea that we could create tangent lines to smooth vector-valued functions. Specifically, we had this definition. We said that as long as it was the case that r prime of t was not the 0 vector, then r prime of t would be referred to as a tangent vector to a curve at a given point. The idea was here that if I have a curve C over in blue, again, at any given point that my r of t would point me to, I could calculate my r prime of t. That creates a tangent vector. Now, I don't know the length of that vector. Its length could actually vary from point to point. But if I wanted to, I could squish that vector down, kind of shrink it back down to this length of a unit vector. Okay? I would refer then to this capital T of t as the unit tangent vector. Notice it's the same r prime of t, but now just divided by its own length to shrink it to a value of 1. So let's take a look at how this would actually work here. All right, if we were to look here at example number 1, you'll see that I have a vector function, r of t, and I'm interested in trying to find the unit tangent vector at the specific time when t is equal to pi over 4. Okay, so if I'm using the above definition, I would just need to be able to establish what r prime is, calculate its norm, and evaluate each of those at pi over 4. All right, so let's start with that. So I'll state here that we calculate r prime of t, and this should be pretty easy to calculate. I got some simple functions here. Derivative of the cosine is the negative sine. Derivative of the sine function is the cosine. And derivative of the t should be equal to 1. All right, so already I can see what I have here. And notice that this actually makes it unbelievably easy to then evaluate this function as well. So I'm going to go ahead and evaluate this right away at the value of pi over 4. And you'll see that that's going to get me negative square root of 2 over 2, positive square root of 2 over 2, and 1. So I already have the vector. I just can't guarantee that this vector is 1 unit long, and so I will need to divide by its norm. Okay. So I can go ahead then and say that the norm for r prime evaluated at pi over 4 would simply be equal to, and I would just need to take each of these values, square them, add them up under a radical. Okay, let's take a look at what we got here. A little bit of simplification can be done. Notice here if I square the root 2 over 2, the top's going to turn into 2, the bottom's going to turn into 4, and so I'm going to end up with a positive 1/2 for each of those, and then plus 1. So it looks like the total length of this curve is simply root 2, or the length of this vector is root 2. So this means that capital T at pi over 4, I know is just r prime at pi over 4 divided by the norm of r prime at pi over 4. And so this is just my negative root 2 over 2, positive root 2 over 2, comma 1, all being divided by that square root 2. Again, I could think about that as like a 1 over a root 2 and simply distribute that or multiply that through my vector. So that would, if I did this, leave me with negative 1/2, positive 1/2, and then I guess 1 over a root 2 over there. Okay, so like, boom, I've done it. I've found this unit tangent vector. Okay. So again, it's just that vector that's on the curve here, and I've just shrunk it down to a size 1. A fairly easy type of calculation to do. In this section, we're going to be looking at 3 different types of vectors we can calculate. This is just the first. This is our unit tangent vector, but in the later videos, we're going to talk about a unit normal and binormal vectors as well.